Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over the relationship between lines in an emission spectrum, wavelength, and also the energy between transitions, electron transitions between different levels. So let's get into this. So in this problem we're told the figure below represents part of the emission spectrum for a 1 electron ion in the gas phase. All the lines result from electronic transitions from excited states to the n equals third state. And then we have a couple of questions. The first question is, what electron transitions correspond to lines A and B? And then the second question is, if the wavelength of line B is 142.5 nanometers, calculate the wavelength of line A. So let's go ahead and answer part A. So we're given this emission spectrum, or a partial emission spectrum, and we're asked, well, what do what transitions do each of these lines refer to? So in order to answer this question, we have to go back to the transition and the different transitions that the electrons can go through and how that relates to the energy and the wavelength. So let's recall that electrons, when they're in their excited state, they jump up to a higher energy level, and then they can relax back down to a lower level. When they relax back down to a lower level, they release energy. And there's a certain amount of energy that's going to be released, and that depends on the distance between the different energy levels, and that distance reflects the difference in the energies of those different levels. So the larger the distance, the larger the energy gap, and so therefore the more energy that's released by the electron that jumps from one level to the other. So you can see here that the jump from n equals 4 to n equals 3 is the smallest gap. So the difference in energy here is going to be the smallest. So then the next one here, the next jump is n equals 5 to n equals 3. And so that's a larger gap here. And so that means more energy difference, a larger energy difference between 5 and 3. So more energy is released when the electron jumps down from 5 to 3 than compared when it jumps down from 4 to 3. And then we could see that also continue here. So going from n equals 6 to n equals 3 is a larger gap. So more energy is going to be released here, and so on. So that's the relationship between the gaps and the energy that the photon is going to have. That photon that's released when the electron jumps from a higher energy to a lower energy, it's going to release the energy in the form of light, a photon, and that photon is going to have a certain wavelength. And so we got to remember what the relationship between wavelength and energy is. So energy is going to be equal to hc over lambda. Lambda is the wavelength. So you could see that the energy difference between the different levels, the energy lost by the electron when it jumps down from one level to the other, is going to be related to the wavelength of light emitted. So it is inversely proportional. That means that the greater the energy lost by the electron, that's going to mean that the smaller the wavelength of the photon that's released. Okay, so let's go back to the question and remind ourselves. It's asking what electronic transitions correspond to lines A and B. So which electron transition corresponds to these two lines here? Well, in order to answer that question, we have to think about what's going on here. So here we're told wavelength is increasing this way. So the wavelength on this side, these bands are corresponding to wavelengths that are smaller. And as you go this way, the lines are corresponding to light waves that have larger or longer wavelengths. Okay? So, so that means that this line here, being the farthest this way, means that this has the longest wavelength. Well, if this is true, if energy and wavelength are inversely proportional, then the longest wavelength is going to correspond with the highest energy of light. Well, the highest energy of light, I'm sorry, not the highest, the lowest energy of light. Getting mixed up. So here we have the wavelength and energy. Here, this band here, this light band here or line corresponds to the longest wavelength. So that means that it's going to correspond with the smallest amount of energy released. So large wavelength, small energy. Remember, wavelength and energy are inversely proportional, they're opposites. So if I know that this is the longest wavelength, then I know that this line corresponds also to the smallest amount of energy. And so we can see here that the smallest amount of energy is between n equals 4 and n equals 3. So this transition right here. And so remember, we're told that all lines result from electronic transitions from excited states down to n equals 3. So they all go down to n equals 3, and they all start at somewhere up here. So the shortest amount of space, the smallest gap in energy is going to be between 4 and 3. So that means that this line must correspond to this transition here from n equals 4 to n equals 3. So that's what this transition is corresponding to. Well, if these bands in the emission spectrum are corresponding to these transitions, and I know that wavelength increases this way, and this is the longest wavelength, and that corresponds to the smallest gap in energy, the smallest difference in energy, then moving this way, if we're getting shorter and shorter wavelengths, that's going to correspond to larger and larger gaps. And so you can see here that the gap between n equals 5 and n equals 3 is the next largest gap. The next larger gap is, or the next smallest gap, I guess, is this between n equals 5 and n equals 3. So that must correspond to the next line in the emission spectrum. So going this way, the next line is B. So that has to correspond to the next transition that's larger in energy. So this has the next largest gap. So that must correspond to the next line in the emission spectrum. So going this way to smaller wavelengths, I'm going to go to next larger energy gap. So this is the energy lost from 5 to 3. So that's going to correspond to this band here. So then B has to be from n equals 5 to n equals 3. And so then the next line, A, has to be the next transition. So because this corresponds to a smaller wavelength than this one, so again, the next gap is going to be this one here. So between n equals 6 and n equals 3, you have larger energy. So that's going to be a smaller wavelength. That's going to correspond to A. So A then has to be the transition from n equals 6 to n equals 3, and so on. So then this one would correspond to the next one. So from transition of n equals 7 to n equals 3. And then this one would correspond to n equals 8 to n equals 3, and so on. And so you can see, notice that as we go higher and higher, the spaces here are closer together, so that the energy difference between successive transitions are going to be closer together. And you can see that the bands of the lines are getting closer together, so the difference in wavelengths are going to be not as large. So this corresponds to this. So I hope that's clear. That's the answer to part A. So based on our understanding of the electron transitions and the relation of the energies of each transition to each other and to the wavelength, we can figure out which band corresponds to what transition. So we were only asked about A and B. So A is going to be the transition from n equals 6 to n equals 3. And B is going to be the transition from n equals 5 to n equals 3. Okay, so that's part A. What about part B? If the wavelength of line B is 142.5 nanometers, calculate the wavelength of line A. Okay, so they're giving us the wavelength of line B, so we can use the Rydberg equation to solve for the Z, the effective nuclear charge. The reason we can use that equation is because they tell us it's a one electron equation, a one electron ion, so therefore it is hydrogen-like, and the Rydberg equation always works with any one electron system, so that makes it us able to solve this problem. Okay, so I'm going to go ahead and erase this to give myself some space. Okay, so let's remind ourselves. So the equation that we're going to use is delta E is equal to negative Z squared times 2.18 times 10 to the negative 18 joules multiplied by 1 over the NF squared minus 1 over NI squared. And just to remind ourselves, Z is the symbol for atomic number. And atomic number, if you remember, is the number of protons in the nucleus. So basically, Z is the measure of the charge on the nucleus. So we call that the effective nuclear charge. And so that's squared. N is representing the energy levels between which the electron is transitioning. So the NF is the final energy level that the electron ends up at, and NI is the initial or starting energy level that it begins at. And so they're squared. So what we can do is, since we're given the wavelength situated with line B, we can use the wavelength and convert that to the energy of the photon from line that is representing line B. So if we can get the energy of the photon, we can use that and plug that into the equation. So let's go ahead and do that. So remember, the energy of the photon is going to be equal to hc over lambda. In this case, we want lambda to be in meters because the speed of light is in meters. And so we're going to have to take the 1 point, we'll do it over here. So I'll do it right here. So we have 142.5 nanometers. And I know that 1 nanometer is 1 billionth of a meter, or 10 to the negative 9 meters, because nano means 1 billionth of. So I'm going to put 1 nanometer on the bottom, and 10 to the negative 9 meters on top. Nanometers cancels out, and so when I do this, I get 1.425 times 10 to the negative 7 meters. So now I have the wavelength in meters. So now I can plug that in along with the Planck's constant in the speed of light. So Planck's constant is 6.626 times 10 to the negative 34 joule seconds. And that's going to be multiplied by the speed of light, which is 3.0 times 10 to the 8 meters per second. And that's going to be divided by the wavelength that we just calculated, 1.425 times 10 to the negative 7 meters. So you can see right away that meters is going to cancel out, seconds are going to cancel out, and we're left with joules. Joules is an energy unit, and that's what we're trying to find, energy of the photon that was released due to the transition of the electron that gave us line B. Okay, let me put line B back. Okay, so when we calculate the energy of the photon, we get, I'm going to go ahead and erase this. What do we get? We get 1.395 times 10 to the negative, I think it was 18 joules. So this is the amount of energy in joules that the photon has that was released from the electron when it did a transition from one energy level to the other. So the energy transition was between, I believe, 5 and 3 for B. Okay, so that's the energy that was released, the energy of the photon released. So now we can use this and plug it into our equation here. Now remember, the energy. This is the energy, the change in energy of the atom. Now the change in energy of the atom is equal to negative the energy of the photon, right? Because the electron is losing energy when it goes from a higher energy level to a lower energy level. So the loss of energy is represented by the negative sign in the change in the energy of the atom. And so that's going to release a photon. And of course, the photon is not going to have negative energy. It's going to have positive energy. So the loss of energy by the atom is the gain of energy that the photon has. So we got to make sure we do this. Otherwise, we're going to get a negative number that we don't want. So that means that if we use this equation, then this is going to be the energy of the change in energy of the atom is going to be minus 1.395 times 10 to the negative 18 joules. Okay, now we're ready to plug in the equation. And so we're going to put in negative 1.395 times 10 to the negative 18 joules is equal to negative z squared times 2.18 times 10 to the negative 18 joules times, and then for the transition, Again, we're looking at line B. We said for line B, the transition was between n equals 5 and n equals 3. So it went from 5 to 3. So the final energy level was 3. So that's going to be 1 over 3 squared minus, and then we have 1 over 5 squared, because the starting energy level was 5. And so now what I can do is I can solve for z. So notice I have negative over here and negative over here. So that's going to become positive because I can divide both sides by the negative and it becomes positive. So that cancels out. And then I can figure this out here, right? So figure that out, subtract these two, multiply by this. And when I do that, I get, so let's do this by step. So here I have 1.395 times 10 to the negative 18 joules equals z squared times 2.18 times 10 to the negative 18 joules. This is going to be 1 over 9 minus 1 over 25. Then I'm going to subtract these two. So then that's 1.395 times 10 to the negative 18 joules equals z squared times 2.18 times 10 to the negative 18 joules. And then when I subtract those, I get 0.071. 0.0711. I'll just put extra ones because they're there. Now I'm going to multiply these two together. So that's going to give me 1.395 times 10 to the negative 18 joules is equal to z squared. And then when I multiply that together, I get 1.550 times 10 to the negative 19 joules. So now all I need to do is divide both sides by this to get z squared by itself. So I'm going to go ahead and erase this since I don't need it anymore. So I have 1.395 times 10 to the negative 18 joules equal to z squared times 1.550 times 10 to the negative 19 joules. Let me double check that calculation. Yep. So now I can divide both sides by 1.550 times 10 to the negative 19 joules. Divide this by 1.550 times 10 to the negative 19 joules. Joules cancels out. And so when I divide that, I get 8. Z squared is equal to 8.9987. So if I take the square root of both sides, then I get z is equal, this is pretty much 9, right? I can round this 9. This is really close to 9. So that means 9 squared. This is going to be approximately very close to 3. So the nuclear charge that's felt by the electron is a 3. So now I know what z is. So I use the information that I got for B to get z. So now I can plug this back into the equation to solve for the wavelength of the line A. But I need to get the change in energy of the atom first. So continuing along, oops. Okay, so now I'm going to go back to the equation. So we're going to go back to the change in energy of the atom is equal to, again, z squared, negative z squared, times 2.18 times 10 to the negative 18 joules times 1 over nf squared minus 1 over ni squared. So now I know what z is. Z is 3. So now I can plug in z. And now we're looking at line A. So remember, for line A, the transition was from 6 to 3. So our initial starting energy level was 6. Our final starting level is, again, 3. So we plug everything and solve like we just did. But this time we're going to solve for the energy change of the atom. So delta E of the atom is going to be equal to negative 3 squared times 2.18 times 10 to the negative 18 joules multiplied by 1 over the final. Again, the final energy level was level number 3. So this is going to be 1 over 3 squared minus, last time it was 1 over 5 squared. In this case, for line A, we started at 6. So this is going to be 1 over 6 squared. And then we do the same thing. We solve the equation. So this is going to be 9 times 2.18. Here, let me bring this down a little bit. Minus 9 times 2.18 times 10 to the negative 18 joules. And then this is going to be 1 over 9 minus 1 over 36. So if I subtract these two, it's going to be equal to minus, minus 9 times 2.18 times 10 to the negative 18 joules. And then if I subtract those, I get 0.083. So 0.08333. There's a lot of threes. And now all I need to do is multiply these three numbers together. And when I do that, I get negative 1.635. So there's going to be a negative 1.635 times 10 to the negative 18 joules. Let me just double check that. Yes. Okay, so now what we have here is the change in the energy of the atom due to the transition of the electron from energy level 6 to energy level 3. Now, that change in the atom's energy is due to the release of energy in a photon, energy of light. So this energy that was lost by the atom was gained by the photon, was released as a photon with that energy. So all we need to do now is use our equation. The energy of the photon is equal to Planck's constant times the speed of light over lambda. So we want to solve for lambda because that's what we're looking for. So when we solve for lambda, that's going to be lambda is equal to hc over the energy of the photon. So we have the energy of the photon, which is the positive part of this. So remember, we said that energy of the photon, the energy of the photon, or the change in energy of the atom, is equal to negative the energy of the photon. So they're opposites of each other. So if this is negative, then the energy of the photon will be positive, right? So we just plug everything in. So we're going to put in 6.626 times 10 to the negative 34, and that's joule seconds, multiplied by the speed of light. Here, let me do this down here so I have space. So lambda is going to be equal to 6.626 times 10 to the negative 34 joule seconds, multiplied by the speed of light, which is 3.0 times 10 to the 8 meters per second, all divided by the energy of the photon, which we got right here, which is going to be a positive value, 1.635 times 10 to the negative 18 joules. Now notice now the joules are going to cancel out. Seconds are going to cancel out. We're left with meters, which is a measure of length, and we're looking for wavelength. So it matches. So then wavelength, if I calculate all this, the wavelength in meters is going to be 1.215 times 10 to the 7th, or 7 here, times 10 to the 7th, or minus 7 meters. And because wavelength of light is usually put in nanometers, we have to convert this to nanometers. So we're going to take 1.2157 times 10 to the negative 7 meters over 1. Again, I know 1 nanometer is equal to 1 times 10 to the negative 9 meters. So I'm going to use that to convert. So I'm going to put 10 to the negative 9 meters on the bottom, and I'm going to put 1 nanometer on top. Meters cancels out. I have nanometers. So then this is going to become 121.6 nanometers. 121.6 nanometers is the wavelength of the light that was emitted in the transition of the electron from 6 to 3, which gave rise to the line A that was in our emission spectrum. I hope this was helpful. If you enjoyed this video, if this helped you any way, then please by all means like the video, share the video, hit that like button somewhere around here, probably over here somewhere. Also, do me a favor, subscribe to my channel, hit that notification bell. When you do, make sure you click all so you'll be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem that you would like help on, or you need a topic you would like me to cover, put that down below. I would like to do that for you. Thanks for joining me, and have a great day.